My name's Charles Hardin, and I'm going to be your software sommelier for this course. So basically, I actually joined Exablox pretty early on, recruited by Doug. Seems he recruited most of us. And I came more from the networking side of things. So I came from a previous networking company, so I kind of look a little bit more at the distributed systems approach of things, and a little bit less, as we used to joke about, the spinning metals of Rust that all the bits were stored on. I just try to get the bits from there to there and everything. So today what we're going to talk about is pretty much an enhancement and a refinement of some data protection work that we had to deal with as part of our architecture. And basically what we came up with was placement groups. So it's very difficult to talk about data protection without talking about failure domains. So basically, they go away. Things disappear. You can't get to them, you can't find them, you don't know where they are, and you're pretty much going to try and recover from that setup. Most everyone agrees on a common set of failure zones. Disk drives, servers, racks, buildings. There are other things that are failure domains, but sometimes they're so large, you just don't care about them. I can guarantee all of you, if the Earth fails, we're not going to worry too much about getting our data. So there is a certain level that you protect to, but there's a level that you just kind of say, yeah, I'm just not going to worry that hard. So this also leads to the hierarchy. The higher up the failure is, the less likely it is you're going to survive it. If you're worried about disk drive failures, but you only have one server, if your server fails, you're not really going to be able to recover from it. So for everyone that is really trying to deal with this, it's basically keeping your data accessible in the presence of a failure. And so now when we actually look at what was happening for us, is we base our architecture on content addressability. That's a fundamental piece and a fundamental foundation for us. That actually decouples the physical location from where we actually place the content. What I mean by that is I could give you a letter, and I could give you the identity of that letter, and it's basically yours. If I ask any of you and you hid it from me, and one of you gave me back that letter, by looking at the identifier, I would know it was the letter that I gave whoever else. So I can basically shuffle all the content around the cluster, and whoever returns it to me, because it matches the identifier, I know it's the content I put into the cluster originally. That actually creates a slight problem for you, because what happens is, in the model, you want to distribute your data across failure domains, so that basically if you have a failure, you can still have the data somewhere else. So when we talk about being able to look up the content, the typical model is a consistent hashing ring. You basically will take a circle, you'll carve the circle up into slices. Wherever your identifier lands, that's the owner. So if I basically landed a hash range, I don't know where I'm pointing. Yeah, if you look at the top of the chart, okay, thanks. Don't worry about it. I'll figure it out later. If you look at the top of the chart, you'll see that the hash range is basically there. So if the identifier landed in that, the owner is the person to the right. And that's pretty much how you can find your object. What this relates to for us is this consistent hashing principle has been used in a lot of places. It's been used in Dynamo, Amazon. It's been used at Swift. A lot of people understand what consistent hashing is, but they most often will do it at the top of the stack. We do it in the middle of the stack. So we build all of our objects for our file system above the ring, and then we distribute all of those objects within the ring. The challenge here is, and this was just basically because everyone else did it, ownership and failover were defined by the ring. If my owner didn't have my data, well, where would I look for it? I just look at the next guy. If he didn't have it, I just look at the next guy. So you basically start walking around the ring looking for your data. The problem here is because the ring doesn't have any notion of where the drives are, you actually can end up with all of your correlated data can end up in the same failure domain. So we obviously augmented this for our data protection. We did some algorithms where we kind of looked at, oh, well, let's place the data not on this node because we already put it there. Let's put it here. But that like looking next just became really problematic because it didn't give us enough flexibility. So what did we do? We wanted to keep the decentralization and all the properties of the consistent hashing ring, But we wanted to fundamentally be able to say the data is owned by these members that are part of different failure domains. So we just split the problem. Any good engineering solution is, if it's too hard to solve, come up with a different answer. So ownership is still defined by the ring, but now what we have is we have a group that we can spread across different failure domains. The best case example is I have 3 servers. What we're ensuring is when we actually place the data in that group, a member is going to be from each different server. So if one server goes offline, we can still get to the data. A member for us is someone that runs our content addressable object store. So that can be anything. Anything that speaks our protocol can be a member of a placement group. The other part about it is a placement group, it is a subsection of the actual key space. What that means is if I have drives of different capacity that are sitting in the cluster, I can actually handle that asymmetry within the cluster because I can make some drives be members of multiple placement groups. So the larger drive would inherently be a member of more groups. So the unit of failure, recovery, is the actual placement group. So as I said, because we allow the asymmetry and allow multiple groups for every drive, when a drive fails, it's going to impact multiple placements. Why that's important, and this is the best refinement that we have, is the optimization was about recovery. Because now we have all these surviving members, the living members, are all actually active and they know who they are. We can actually run recovery independently and in parallel. So, for instance, quick simple math. If I lost a terabyte of data, that drive went away, and that drive was a member of 10 placement groups, I always use powers of 10 because my math is bad, then that only means that I have to transfer basically 100 gigabytes of data from 9 other members, okay? And that can be done in parallel. So this is basically the actual algorithm. Once the cluster realizes a drive is gone, it's been marked as failed. So now we have the surviving members, which is 2. So we're going to choose a new member, and that's based upon our policy. So that's based upon like how big the cluster is, how many drives there are, what the composition is of the cluster. And that's basically where the cluster is now going to say, hey, I want to re-protect this data set with this placement group onto this member over here. Then what it does is we have a peer-to-peer transfer mechanism, which is actually kind of the benefit is that we can do this all in parallel. Because again, we can just move content around, and that content is still the same content even when it shows up in another drive. So now we're basically going to go to add a new member. We're going to ask the other members to now transfer their content for their placement groups to the new member, and it doesn't even change the ring or the location because the placement group is what changed. We didn't have to change any data distribution. We didn't have to change any topology. All of the asynchronicity of the consistent hashing properties still hold. So feel free to ask any questions. That's probably why we hold it for this slide. I'm not sure how many of you have ever played this game. It's a rather fun game. It's called the Towers of Hanoi. And what on earth does this have to do with storage? So if you looked at each failure domain as kind of like a little tower, we're basically going to end up placing our data onto our little towers. Well, the problem is that when you lose a disk, your data is basically off somewhere else, and you can't get to it anymore. So your data protection level has been degraded, which, by the way, is a pretty horrid term. If anyone has a better name than degraded, much appreciate it. But we want to basically
Suboptimal?
Suboptimal. Ooh, that actually is pretty good.
No charge.
So basically what we want to do is we want to re-protect the data and relay it out so it once again reaches the data protection. So the rules of this game are actually pretty simple. Place the data you just lost onto another tower, but you can't have any matching colors. And for those of you that are colorblind, I apologize in advance. So basically, it sounds pretty simple because now you put the orange and the green data onto 2 towers that don't have orange and green already. And now you're in the process of moving the cyan, but another disk fails. And this is the reality of a scale-out system. If you're successful in scaling out, you just get bigger and bigger and bigger. You keep encompassing more and more entities that can fail. And so if you are truly successful to scaling out to, let's say, 1 million drives, you should be prepared that if you have a 0.1% failure rate, you're in a constant state of failure. You are constantly doing it. And that's actually one of those interesting premises that when you deal with distributed systems, you don't think about it the first time you go through it, because you're just thinking, oh, I'm just building a simple 3-node cluster. I'm using 5 disks. But now all of a sudden we have customers that quickly, and we architecturally, we're supporting 100 disks. So if you imagine this problem amplified to the point where you have 100 disks, that's actually the reality of that is reality. Because there is no now, there is no a snapshot in time that says I can literally pick this up and move this here instantaneously. Recovery is something that does take a matter of time. I have to continually increase my recovery windows so that I can recover the data before the next failure occurs. And that is basically the ultimate goal of placement groups. So the quick model that we've actually been trying to get at is, and this is what it goes back to, is if I had the 2 surviving members that actually had the data copies that I wanted, if you wanted to look at the actual model, if this is now the new member, it would be how quickly can I read from here and how quickly can I write to here. The minimum of that, so if I can only read at 1 megabyte a second, but I can write at 100 megabytes a second, the minimum amount of time that it takes me to transfer the data is going to be how long it takes me to recover. So clearly, the more of these I add in, the more in parallel I can read at the time. And that's actually why you want to have placement groups so that we can dynamically adjust the membership set to meet the recovery time guarantees that we want. The only other problem that you have is all the stuff in between. So if you did a very simple model where you took like 2 SSDs and said I'm going to recover to the other one, and you looked at that math, you'd be like, oh my god, this is fantastic. I can like read SSDs at 400 megabytes a second, and I can write to an SSD at 400 megabytes a second. My recovery window is going to be like that. Only challenge with that is there's typically a network in between. So you typically become networking limited. You typically become limited by resource contention because other things are actually running. And so you basically still have to deal with that. So we deal in the real world, but the model is to actually accomplish the objective, which is have multiple sources that can contribute to recover your data, and ultimately, you only have to recover the amount of data that you lost. So if you lost a terabyte, you're only moving a terabyte of data.
Can you talk about when you scale out capacity, how that pertains to placement groups as far as managing storage going forward in the failure domains?
Oh, yes. So basically, when you add a new SSD, you basically model this as a CA store, CA object store. Okay? When this guy gets carved up, just think of it this way. And this is, it's hard to draw because it's kind of the logical way to look at it. This isn't actually physically what we do. We don't start at the top and slice it up. But what we're doing in here is we're slicing and dicing this SSD up into little PG IDs, which is this slice is going to go here, this slice can go here, this slice can go here. So now I have this new capacity, which means that what I can do is without changing the ring placement, without changing the ring topology at all, I just go into the owners and I take this slice and I now assign him to that owner. I take this slice and I now assign him to this owner. Sorry, these should be circles. And so what's going on here is I'm building out these little placement group sets with the new capacity. As we now fill this data up from the ring, because we're now actually seeding it, because we're basically saying, okay, fine, we're going to use you, we'll add you as a member. We can then go back through and basically drop off an old member, and basically now reuse that placement somewhere else. If we want to, but this actually requires more movement of the entire data topology, we can actually introduce a new owner as well. So there's 2 ways for us to basically add capacity. We can add capacity without impacting any of the data in your system, or we can add a new ownership because there's now basically a new failure domain, and it actually is more conducive for us to scale out to a larger key space for another range set for the other members. Okay?
And Charles, when you say impacting the data, it's not the availability of the data, it's whether we move those objects to different PGs.
Yes. It's basically what you're trying to do is you're trying to conserve work. You don't want to move data if you don't have to, because again, you have user I/O going on in the foreground, you have other background tasks, you have other resources that need to use the cluster. And the challenge is if you get too ahead of yourself, you're basically going to start doing a lot more work in this than you actually need to, which is going to take away resources from something else. And then the user might actually impact it. Because as we always say, the ideal part for a storage is the user never knows you're there, which kind of hurts a little, but that's basically what it seems like.
It's not personal, Charles.
No.
So how big are the slices for disk?
They're configurable, and so right now, and so this is a tuning, so I'm going to tell you what it is today. By the time this video gets released, I can almost guarantee you it will be different. So right now, we are tuning them at 128 megs, I believe, but they may actually be getting a little bit bigger than that. It just depends upon what the outcome is.
Yeah, it's based on the drive size, I guess.
Yeah, so basically, the bigger the drive is, the more we'll slice it, and then the more that it'll become a member of.
Yeah, okay.
Is it the same chunk size as like the deduplication block?
So this is actually where it gets hard. The chunk size this isn't actually physical, this is key space wise. So the key doesn't define a chunk. What it just means is that out of the range of the hashes that we're going to use, these hashes are assigned to that guy. If that runs out of space, that's effectively when we add a new owner because we no longer have enough space for that hash range. So now we're going to allocate another owner so we can distribute the hashes evenly amongst the survivors. However, if we're within space, then we just fill it up until, because we still have space. So we just keep adding hashes into that.
And then when you have this hash space split, I'll call it,
Yeah.
do you link the old one to the new one, or is it just reallocate the hash space between those two?
No, it's only to impact where you sliced it. So basically, if you take the slice of your pie, and if you cut it in there, the only thing that's basically is getting impacted is the movement within that slice. So if you do it correctly, which we will do, what you will basically have is you'll have a union where you have the set of the old guys and you'll have a set of the new guys. You just kind of split that and then just add members to both to get your space back up. And that's one of the coolest parts about this is having the ability to basically decouple physical constraints from just where you place the objects makes the implementation really elegant. It really scales out capacity. So as you contribute SSDs, and that's why the SSD setup is so amazing, the performance of it is so high that you literally expect the fact that you're still implementing a key value store style protocol, it's content addressable key value store. Even though you're implementing key value store, your IOPS are still high enough to be within a reasonable approach to legacy storage.
And Ray, our objects they vary based upon what the file and what the variable length dedupe segment size is. So they'll vary from a few.
Sorry, I just want to be careful. We do variable length chunking. You can't turn dedupe off. That was probably one of the best customer reactions we ever got. I was like, how do I turn the dedupe off? It's like, you can't. Because we have a content addressable store, if you store the same content, it's deduped automatically. And that's what Sean meant by free, even though it's not free. It's a cost we pay. And the reason why you pay that cost is because it's so elegant. It's the fact that you can put that content anywhere. You can redistribute it everywhere. And so the variable length chunking is actually just a function of that's more efficient for compression. The moment you introduce compression, you have variable block sizes. And that's just a factor of reality. Any file system that does compression, you go from fixed size blocks to variable size blocks. So when we did the compression, we did variable length chunking too. And so that variable length chunking just allows it to get stored as, different offsets from 1 byte to basically 1 megabyte.